Okay, for what we have in the realm of working with geometric concepts along the lines of matrices and determinants. Okay, and we have for this section, okay, we have area, volume, and equations of lines and planes. And among the topics we have in working with matrices and determinants is going to be the configuration of the area of a triangle in the xy plane. And we have for the area of a triangle that consists of vertices, okay, where we have the order pairs x1, y1, x2, y2, and x3, y3 is going to be where we have in terms of matrices and determinants, okay, will be equal to plus or minus 1/2 of the determinant of the matrix, okay, that consists of, in the first row, you had the first vertex followed by 1, second vertex followed by 1, and then we had the coordinates of the last vertex followed by 1. So you had the last column consisting of the exclusive value of 1. And again, the plus or minus 1/2, this will be what we have in terms of safeguarding the result in becoming a positive value. Like in case of the determinant value being negative, you're going to apply negative 1/2. And just as an example for determining the area of a triangle, and let's say that we have the vertices, okay, to be -2, 5, 0, -1, and 3, -9. Okay, so for the matrix A, okay, so you have x01, y01, 1, and that is going to be -2, 5, and 1. x2, y2, 1 will be 0, -1, and 1. And for the last vertex coordinates followed by 1, we have 3, -9, and 1. And looking at the value of the determinant, okay, so we have for the determinant of A, again, so you're looking at alternating sign values among the cofactors and minors. So we have like the plus application of -2 times the minor of the first row, first column. So we have consisting of, in the 2 by 2 determinant, the values -1 and 1, -9 and 1. Then we have -5 times the 2 by 2 consisting of 0, 1, 3, and 1. And then we have +1, and you have the minor of the first row, last column, with 0, -1, 3, and -9. And so we have in the follow through, we have -2. And for the determinant of the first 2 by 2 array, okay, we have 8. Then we have -5 times the next determinant, which we have at -3. And then we have +1 times the last of the 2 by 2 determinant values, which is 3. And we have -16, and what's going to be +15, and we have +3 is equal to 2. So that is going to be the value of the determinant of A. And so for the area, okay, we have, again, plus or minus 1/2 of the determinant value of A. And with the determinant value at 2, and we want the area to be a positive numerical value, so we're going to take positive 1/2 times 2, and we're going to have the area of this particular triangle to end up at 1. Okay, now for the next topic, okay, and we have for the test for collinear points in the xy plane. And we have 3 points, x1, y1, x2, y2, and x3, y3 are collinear if and only if the determinant of what we have among the 3 points, okay, is going to be equal to 0. So you have in the lineup, you have the first column with x1, x2, x3, next column y01, y02, y3, and the last column again solely with the value of 1. And let's say that if we have our 3 points to be 1, 4, 3, 4, and 5, 4. Okay, so we have in the layout, okay, for x1, x2, x3, we have 1, 3, 5. y1, y2, y3 will be exclusively of the value 4. And again, we had the last column to consist of 1. And just following through, so you got +1. And then we had the 2 by 2 array set up with 4, 1, 4, 1. And then we have -4, and the minor of the first row, second column, we have consisting of 3, 1, 5, 1, and then we have +1 times the minor. We have the first row, last column, where we have 3, 4, and 5, 4. And for these 2 by 2 setups, okay, we have for the determinant values Okay, we have 1 times what is going to be 0. And we have minus 4 times what is going to be negative 2. And we have plus 1 times what is going to be negative 8. And guess what? We have 0 and what's going to be plus 8. And then in turn, minus 8. And that is equal to 0. And since the value of the determinant is equal to 0, it's going to turn out that 1, 3, 5, 4, and 5, 4 will all be collinear. Okay, now if we look at modifying, okay, the third point, going from 5, 4 to 5, 5, and to see if the points 1, 4, 3, 4, and 5, 5 are collinear. So our matrix A we have consisting of 1, 3, 5, 4, 4, 5, and 1, 1, 1 as we go from the first to the last columns. And for the value of the determinant, okay, so you have like plus 1 times 4, 1, 5, 1, and then we have minus 4 times the 2 by 2 array consisting of 3, 1, 5, 1, and we have plus 1 times the 2 by 2 array determinant where we have consisting of 3, 4, 5, 5, and looking at the values, okay, so we have 1 times negative 1, minus 4 times what is going to be negative 2, and we have plus 1 times what is going to be negative 5. So here we're going to have negative 1 plus 8 is 7, and 7 minus 5 comes out to 2, which is not equal to 0. And since the value of this determinant does not equal to 0, these points will not be all collinear. All right, now for the next item, okay, we have for the 2-point form of an equation of a line. And now there have been topics, say in Math 171, where you're looking at stuff like the determination of slope and the point slope form of the equation of a line, leading to the slope-intercept form of the equation of a line, and that can also be written in standard form. Now, in the realm of what we have in the world of matrices and determinants, we have in this approach an equation of the line passing through the distinct points x01, y01, and x2, y2 is going to be where the value of the determinant. And you have, for the first row, you have the letters x, y, and 1. Middle row, you have, again, the coordinates. We have x1, y1, followed by 1. And then we have, for the second point, we have x2, y2 coordinates in the last row, followed by 1. And the value of the determinant is going to be equal to 0. And we are going to form the necessary coefficients for the x and the y terms to establish or to ensure that the value of the determinant is equal to 0. Okay, and just as an example, let's say that if you have 2 points, negative 2, 5, and 3, negative 9. So for the first row in the matrix A, okay, we'll have x, y, 1. And the second row we have, for the first point, we have the coordinates x at negative 2, y at 5, and again we have 1 to follow. And for the second point through which the line is going to pass, okay, we have the x value at 3, the y value at negative 9, and we have followed by 1. And looking at the value of what we have in the case of the determinant, and we're going to make sure that this is equal to 0. So we have in our setup, okay, so just breaking this up into 2 by 2 determinant portions. Okay, so going column by column, so you have like plus x, minus y, and plus 1. And for the first row, first column, minor, okay, you have 5 and 1, negative 9 and 1. And for the first row, second column, minor, we have negative 2, 1, 3 and 1. And for the setup in the minor for the first row, third column, okay, we have negative 2 and 5, 3, and negative 9. And so we have x, and for the first 2 by 2 determinant, and we have what's going to be 5 plus 9, which is 14. And we have minus y times, and what's going to be negative 2 minus 3, which is negative 5. And we have plus 1, which is going to be 18 minus 15, which is 3. All right, so you have x times 14 minus y times negative 5 plus 1 times 3 is equal to 0. And just multiply. So you got 14x plus 5y plus 3 is equal to 0. And putting in standard form, so we're going to have 14x plus 5y equals negative 3 will be the equation. And you can sort of go back and check, like if x is negative 2 and y is 5, 14 times negative 2 is negative 28. 5 times 5 is 25, negative 28 plus 25 is negative 3. And for x at 3, y at negative 9, 14 times 3 is 42. 5 times negative 9 is negative 45. And 42 and negative 45 will also form negative 3. Now, looking at the volume of a tetrahedron that consists of 4 vertices, okay, and the volume of a tetrahedron, where we have in the x, y, and z coordinate system, and the volume of a tetrahedron with the vertices x1, y1, z1, all the way to x of 4, y of 4, z of 4, is going to be equal to plus or minus 1/6 of the determinant of what we have going with the matrix, okay, where we have consisting of the first coordinates followed by 1 in the top row, second coordinates followed by 1 in the next, and then we have the third point coordinates followed by 1 in the next to last row, and of course the bottom row we have with the last set of coordinates followed by 1. And just like the area of a triangle, you're going to apply either plus or minus to ensure that the given measure is positive, where in this case we'll have a positive volume for a tetrahedron, just like we had a positive area for a triangle. And just a sample of looking for the volume of a tetrahedron. And let's say that if you're determining one that has, or determining the volume of a tetrahedron that has the vertices 2, 0, 0, 0, 2, 0, 0, 0, 2, and 1, 1, and 1. Okay, so this is going to be your matrix. Okay, so just going at it point by point. So we have 2, 0, 0 followed by 1. Next we have 0, 2, 0 followed by 1. Then we have 0, 0, 2 followed by 1. And then we have last 1, 1, 1. And then closing out with 1. And if we're looking for the value of the determinant, okay, so just some of the operations here. I want to get this as close to an identity as much as possible, kind of like in performing sort of like reduced row echelon form, but I'm going to be looking at factoring out in the process, okay? Like I want the upper left-hand number to be 1, so I'm going to factor out 2 from the first row. So in the modification, so 2 will be brought out to the front, and the top row is going to be adjusted to 1, 0, 0, and 1/2. And notice in the first column, I want to make this leading 1 in the bottom row to be 0. And I can follow through upon subtracting the first row elements from the last. So in this case, we're going to have 2, and the change up is going to be with the bottom. We're going to have 0, followed by 1, followed by another 1. And 1 minus 1/2 leads to 1/2 on the bottom. Okay, now if I look into the next row, so I have another 2. And if I factor this out, just like I did with the upper left-hand 2, so if I factor out another 2, leading coefficient is going to be 4, and the change up in the second row we have 0, 1, 0, 1/2. Everything else remaining fixed. And looking at what we have in the process, if you notice, okay, I want the second column to consist of 0, 1, 0, and 0. So I want to make the first one that appears in the bottom row at this stage to go to 0. So I'm going to take the second row elements away from the last. And so the bottom row in this case is going to change over to 0, 0, 1, and 1/2 minus 1/2 goes to 0. And looking and proceeding on down to the third row, so I have a 2 at the front. I want to change this to a 1, and I'm going to factor out 2 once more. So the leading coefficient in front of the determinant is going to be at 8. 4 times 2 is 8. And changing up what I have in the third row, so I now have 0, 0, 1, and 1/2. And then changing the 1 that remains in the bottom row. To get that out, I'm going to take away the third row elements away from the last row. And in this case, we have 8 times. And again, you have in the bottom row, you have the change up. You got 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 1 is 0, and now we have 0 minus 1/2 is negative 1/2. And for what we have at this stage, I want to change this negative 1/2 over to 1. So I'm going to factor out negative 1/2 from the last row. And so -1/2 times 8 is -4. And the bottom row we have 0, 0, 0, and 1. And ultimately, I can perform the necessary row operations whereupon I'm going to change these 1/2s immediately above to 0. And so, in other words, like you have like R1 minus 1/2 of R4, R2 minus 1/2 of R4, RF3 minus 1/2 of R4. And so you have left over, you have just this diagonal array of 1s amongst the 0s. And so that is going to be our identity, and this portion goes to 1. So for the value of the determinant of this matrix, this will be -4 times 1, which is -4. And for the volume of the tetrahedron, okay, since the value of the determinant is negative, I'm going to apply -1/6 to ensure a positive product. And for this particular tetrahedron, the volume is going to end up at 2/3.